In Chapter 18, we introduced the parallel plate capacitor, which is composed of two metal plates near each other, separated by a small distance. However, capacitors can come in many shapes and sizes, and in general, a capacitor consists of two conductors of any shape placed near one another without touching. The main function of a capacitor is to store charge, and each plate carries a charge of the same magnitude, one positive and one negative. One simple way to charge a capacitor is to connect it to a battery. We will see in the chapter on DC circuits that a battery acts like a pump. It pulls electrons off one of the plates and pushes them on the other. The voltage of the battery plays the role of the pump pressure. The greater the voltage, the more charge the battery can transfer. Therefore, the magnitude of the charge on each plate will be directly proportional to the voltage. We can make this an equality with the addition of a proportionality constant C, which is known as the capacitance of the capacitor. The larger the capacitance, the greater the amount of charge the capacitor can hold for a given voltage. The SI unit of capacitance is a coulomb per volt, which is a farad. The unit of capacitance is named after Michael Faraday, who was an English scientist who contributed to the field of electromagnetism, which we will study later in the course. 1 farad is an enormously large capacitance. In most electronic devices, capacitors have values that are much smaller, such as microfarads, 1 times 10 to the minus 6, and picofarads, 1 times 10 to the minus 12. The space between the plates of a capacitor can be empty, but often it is filled with an electrically insulating material known as a dielectric. As we will see, the reason to do this is that the dielectric can markedly increase the capacitance of the capacitor and allow it to store more charge. The dielectric creates this effect because of the way it alters the electric field between the plates. The figure shows a charged capacitor that is empty. A uniform electric field exists between the plates that points from the positive plate to the negative one. Once a dielectric is inserted between the plates, the charges in the molecules of the insulator are not free to move, as they would be in a conductor. However, they shift their position slightly in response to the capacitor's electric field. The electrons move toward the positive plate, and the positive charge in the molecules shifts toward the negative plate. This slight separation of charge creates molecular dipoles through the process of polarization. Each of the dipoles now creates an internal electric field of their own that points in a direction opposite to that of the capacitor's electric field, thereby reducing the net electric field between the plates, assuming the charge on the plates remains constant. This reduction in the electric field is described by the dielectric constant kappa, which is defined as the ratio of the electric field without the dielectric to the field with the dielectric. Since kappa is the ratio of two electric fields, it is a unitless number. And since E0 is greater than E, kappa will be greater than or equal to 1. The value of the dielectric constant is material dependent. The table below shows the dielectric constants for some common substances. Besides the dielectric, the geometry of the plates also affects the capacitance. Consider the figure below of a parallel plate capacitor with plate area A and separation distance d. A dielectric between the plates has a dielectric constant kappa. The electric field inside the dielectric will be equal to V over d, where V is the magnitude of the potential difference between the plates. If the charge on each plate is kept fixed, then the relationship between the electric field inside the dielectric to the electric field without the dielectric is given by the following. We have already shown that the electric field between the plates without the dielectric is given by Q over epsilon naught times A. Making the substitution and regrouping, we get the following expression. Notice it is written in the form of Q equals a constant times V. Comparing this to Q equals CV, we see that the constant in parentheses must be equal to the capacitance. The capacitance is only affected by its geometry, A and D, and by the dielectric constant. If the space between the plates is empty, then kappa will be equal to 1, and C will be equal to kappa times C0. This relationship applies to any capacitor, not just to the parallel plate type. And it shows why you would want to add a dielectric to a capacitor. It increases the capacitance, and thus the amount of charge it can hold. In addition to storing charge, a capacitor also stores energy. The stored electrostatic potential energy in a capacitor arises because a battery that transfers the charge from one plate to another must do work to move the charge. The work done is equal to the product of the charge times the potential difference between the plates. However, as each increment of charge is moved, the potential difference increases slightly, and a larger amount of work is needed to move the next amount of charge. The total work done in completely charging the capacitor is equal to the product of the total charge transferred and the average potential difference. Since the average potential difference is 1/2 the final potential, the total work done by the battery is given by the following. This work does not disappear, but is stored as electrostatic potential energy in the capacitor, so that the energy is equal to 1/2 Q times V. We can solve the relationship Q equals CV for either Q or V, and then make this substitution into the energy equation above. This gives us two more equivalent ways to calculate the energy. We can also consider the energy as being stored in the electric field between the plates. By substituting V is equal to E times D and C equals kappa epsilon naught A over D into the energy equation E equals 1/2 CV squared, we get the following. Notice the product of the area A of each plate times D, the distance between them, is just the volume of space between the plates. Dividing both sides of this relationship by the volume gives us the energy per unit volume, or the energy density. Notice that the energy density goes as the square of the electric field, and this is true for any electric field, not just the electric field of a parallel plate capacitor.